If this is the center of curvature, half of the center of curvature will be equal to what? Half of the center of curvature is equal to
the focal point.
The focal point or the principal focus. So this is F. So if you incident a ray of light and the ray is parallel to the principal focus, what will happen? If the ray is parallel to the principal focus after reflection, what will happen?
It must pass through the focal length.
It must pass through the focal point.
Hey,
Schneider, mute yourself. Schneider. Let me control it here. Okay. So if the ray is parallel to the principal focus, after reflection, it must pass through the principal. If it's parallel to the principal axis, after reflection, it must pass through F. So this is 1, 2. 2. Two. A ray of light which is passing through F or coming from F, after reflection, what must happen? Yes, class, if the ray is passing through F or coming from F, after reflection, what will happen?
It must be parallel to the principal axis.
Thank you. So once the ray passes through F, after reflection, the reflected ray must be parallel to the principal axis, like this. Now this is the second rule. Then the third rule. A ray of light now let me indicate all this point before. A ray of light which incidents on the mirror at 90 after must pass through the center of curvature and then reflect along the same path. So incident, reflection. So when you see a ray of light passing through the center of curvature C, then it means that the ray is hitting on the mirror at an angle of 90 from that direction. Then the fourth rule. So if this is P, C, center of curvature is here, and we have half of this being F. The last rule says that a ray of light hitting the pole must also reflect at the same axis. Must reflect at the same axis. Or it must be symmetrical. Meaning these two angles must be the same. Now note that the rules do not only apply to concave. These are how the rules look like on concave or converging mirrors. Let's look at how it works when the mirror is convex. When the mirror is a convex mirror, how does these rules also apply? So for convex mirror, the reflecting surface curves outwardly. So this is the center, the pole. The center of curvature and the principal focus are all behind the mirror. Ella. Okay. I was calling you earlier, but the response wasn't coming. So this is F. All right. So a ray of light, let me extend the principal axis to the other end. So we can draw our parallel lines better. So a ray of light traveling parallel to the principal axis. How will it behave after reflection? Yes, class, how will this ray behave after reflection? Yes. A ray of light parallel to the principal axis, how will it behave after reflection? Ella, help us. How will the ray behave after reflection? Ella, are you there? Aziz. Aziz.
Yes, sir.
How would the ray behave after reflection on the principal, on the convex mirror?
So it will pass through the focal point.
No, I won't buy that. Kwabena Yameche,
Yes, sir.
what will happen after reflection?
Sir, please, I'm not sure of my. Talking
Uh,
about the ray at the top.
pardon?
The ray at the top.
Yes, when
The ray
the parallel ray incident on the mirror, what will happen?
Sir, please, I'm not sure of my question, but once it reflects, like the ray becomes, I don't know, wide or something like that.
It will diverge, but how will it diverge? Okay, let me hear from other colleagues. So, Cliff, share what you think with us. What do you think will happen after reflection from the mirror?
Please, I initially thought it would pass through the focal point.
You are not wrong, but how you are actually putting it is the issue. Okay, so let's carry on. Now, convex mirrors diverge reflected rays. Okay, so the ray will be diverged, but the diverged ray or the diverted ray will appear to be diverted from F. Okay, it won't, you can't say it will pass through, but because it's a virtual thing, So the reflected ray will be diverted, but the diverted ray would appear to be diverted from a point on the principal axis. And this point is what we call as a focal point. And this explains the reason why the focal point of convex mirror is virtual. Because the diverted ray appears to be diverted from a point on the principal axis, which is the focal point. Class, are you okay?
Yes, sir.
So in most cases, we even represent the focal point. The line drawn from the focal point is virtual. Ella, then Emanuela, rejoin. If you cannot hear me, rejoin, okay? This line is drawn using broken lines because it's a virtual point. So if you incident numerous parallel beam to it, this is how it will behave. One, a ray which is parallel to it will be diverted. But the diverted ray appears to be diverted from a point on the principal axis. And this point is known as the focal point or the principal focus of the mirror. So, Aziz,
Yes, sir.
if you are asked to define the principal focus of a convex mirror, how would you define this? Define the principal focus of a convex mirror. How would you do that?
It is where parallel rays meet. It is where parallel rays meet.
Aziz, I won't buy it. Okay, more views. Bright, define the principal focus of a convex mirror. Bright. Yeah, Ella.
So please, the
Hey,
principal focus of a convex mirror is the point on the principal axis where all the parallel rays close to the principal axis appear to be divergent after hitting the focal point
Appear to be diverted from.
from the
Okay, from is very important. So you see these two reflected rays, this one and this one, they all appear to be diverted from a point on the principal focus, and that point becomes a point on the principal axis, which becomes the principal focus. Class, are you okay? So whenever we are actually marking, we look at all these key attributes. If you don't bring it, then it's a problem. So please take note of the key concepts we expect. Aziz, right? Kwabna Yamicha and the rest of you, are you okay?
Sir.
Okay. All right. So let's look at the second rule and how it works for convex. A ray of light which appears to pass through F. Don't forget, F is not real, so you can't say that which passes through F. Here, F is virtual, so a ray of light which appears to pass through F, meaning that we have this ray coming from above. Look at the direction. So there's a source. Benjamin, mute yourself. So this ray, you see, appears to be passing through F. And once it appears to pass through F, after incidenting on the mirror, what do you think will happen? When it appears to pass through F after reflection, what will happen, class? Share your views. Share your views with us. If the ray appears to pass through F after reflection, what will happen? Kwabena Yameche. Kwabena Yameche.
Yes, sir.
Yes, if the ray appears to pass through F after reflection, what do you think will happen? Bright.
The
Mm,
ray will die.
Let's hurry up in our opinion, sharing of opinion, please.
The ray will diverge onto the mirror again and then
Kwabena,
reflect this line.
it is already diverted. What is coming in appears diverted already. So when it hits on the mirror, what will happen after its interaction with the mirror? That's the question. Bright.
Sometimes I think the ray becomes parallel to the
Exactly.
principal.
Exactly. Okay, it is the opposite of the first rule. The first rule, please, everybody should pay attention. The first rule, 1, we have parallel ray after hitting the mirror, diverted and appears to be diverted from F. Then we have the ray which is already diverted appearing to be passing through F. And so after reflection, the reflected ray must this time be parallel to the principal axis. So it obeys the principle of reversibility of light. So the reflected ray must be parallel to the principal axis. It's just the opposite of the first one. This is the second rule. Then the third rule, so this is C, half of C, this half of PCS, where the focal point is. A ray of light which appears to, a ray of light hitting the mirror at 90 would pass through C and reflect back along the same path. So incident, reflection. So when you see 2 arrows along the same line, then it means the ray is hitting the mirror at 90 and as a result must pass through C. Please, all rays at the back of the mirror must be broken line. Must be broken line. I don't have that. That is why it appears to look like a solid line. Are you okay? Ella, are you there?
Yes, please.
You are not talking again. Hepzibah is not talking. She will say that, oh, the microphone cannot microphone. And then the last rule. See half of it. Please, when you are drawing this, take your measurement. Take measurements. I lack the technology. That's why I'm not measuring.
I'm sorry.
Ohima was sorry. Mute your mic. So when a ray of light hits the pole, it must reflect in that symmetrical form. When it hits the pole, the reflected ray must be symmetrical. So incident and then reflected. So this these are how the rules apply for convex too. For convex mirror as well. Okay. Ray diagrams must be done using straight edge. Kwabena Yameche, can you hear me?
Yes, sir.
I am asking because of your message on the chat thing. All right. So let's begin. Formation of images as we vary object position. Formation of images on concave mirror when we finish convex mirror. Then apply the rules to see how the image will look like. So I want us to start. Let's place the object beyond the center of curvature, beyond C. So the question is, using ray diagram, describe the nature of the image formed when objects is placed beyond C. So object is placed beyond the center of curvature, beyond C. Okay. Beyond C can also be described as object between infinity and C. So it means that the object is somewhere here. Any position behind C is where the object is. Now, in ray diagrams, we don't want to draw a mirror with a very large aperture. So what we do is that we rule a vertical line behind the mirror, which will cater for reflection of light, which goes beyond the aperture of the mirror. So it will cater for reflections which go beyond the aperture. So let's apply the rule. 1. A ray of light parallel to the principal axis. After reflection, what must happen, Ella? Parallel to the...
It passes through the focal point.
So it must reflect and pass through the focal point. Okay, so let me change the colors. The reflected rays will be denoted using color red. So this reflected ray must pass through F. You just need 2 rules, and it can be any of it. A ray of light hitting the mirror at 90 must pass through C and reflect along the same path. So incident reflected. When you draw a ray without arrow, you are digging your own grave. We'll bury you. Benjamin, I'll mute you. Now, where two reflected rays meet or intersect, that is where the head of the image will be. Okay. Note that the foot of the object and the head and the image is always on the principal axis. So where two reflected rays intersect, that is the point where the head of the image would also be. So this is I, the image. O, which is the object. Class, do we all understand? Do we all understand? Hey, no response. Are we okay?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so let's describe this image. How the image is. One, per what you've seen, the image, how would you describe the image? One, yes?
Sir, please, it is real.
So image is real. Ella,
Sir, please, the image is diminished.
okay. And please note that all real images are also inverted. All real images are inverted. All virtual images are upright. So image is real. Once it's real, then it means that image is inverted. Ella said image is diminished. Ella, if you say that image is diminished, what do you mean?
Sir, please, in simple terms, I'm trying to say that the image is smaller than the object.
The size of the image is smaller than the size of the object. And then lastly, what is the last observation? Right, you were trying to contribute. Okay, so the last observation is the precise location of the image. Image is formed between the center of curvature and the focal point. So image is between C and F. All right. A word search for you right away. 2. Object is at the center of curvature. Object is at C. So within 3 minutes, do this, after which I will discuss with you. Start work. Object placed at C. Start work, everybody. So use ray diagrams to describe the nature of the image formed when object is at C. Are we on it? Class, are you on? You have 1 minute more. 1 minute more to go. Hello, Stephen. Good morning. Let's look at it. So when you are doing this, please, the first consideration is that the relationship between the radius of curvature and then the focal point, focal length must be taken or must be adhered to seriously. If you don't do that, it will affect. So if you take PC as maybe 10, then note that F will be equal to 5. You must take the measurement very well. Take it, measure it accurately, else it will affect your. Okay. So having done that, place the object at C. And use the rules. So a ray of light traveling from the object traveling parallel to the principal axis after reflection must reflect and pass through F. That's one. If you draw a ray without arrows, You are just drawing lines. Then 2, a ray of light from the object passing through F after reflection, the reflected ray must be parallel to the principal axis. You must ensure that you are actually drawing a parallel line, else it will affect the precise location. So incident reflected. This is where the two intersect. And that will be where the head is. Good. So let's describe the nature of the image formed. 1. Yes. Let's describe the nature of the image formed. And I want contribution from Ella. 1.
Please, the image size is the same as the object size.
So image is the same as objects. Fantastic. 2. Yes, I'm waiting for contributions from you. Let's. Mhm.
It is inverted.
Yes, once image is. Before you talk about inversion, talk about whether it is real or virtual first. Okay. Right, rejoin. If you can't hear me, I think it will be a network problem. Rejoin. So is the image real or virtual, class?
Real.
It's re-
So image,
real.
yes. Image is real. Then once it's real, then you can talk about inversion. Last one. What is the last observation? What is the last observation? There is a very important, yes, Ella.
The image is formed at the center of curvature.
So image is formed at C. Thank you. So the only point where an object will form an image at the same location is when it is at C. The size will be the same. The position will also be the same. So take note. These things you must know by heart. Okay. Kwabena, Nyameche, and the rest of you, are you there?
Yes, sir.
I hope you are following. Okay, let's then bring the object between C and F. Object is now between C and F. So I'm giving this work, though you are all to attempt it, but I'm giving this work to Kwabena Nyameche so that when you finish, you discuss what you got with us. Object is between C and F. Use ray diagram to describe the nature of the image form. The rest of you must also do it, but I'll pick Kwabene's answers. So start work. 3 minutes. Object is between C and F. Okay, let me share let me share. So, Kwabla Yamiche, your object is between C and F. Asada and Ella, Hefzibah, object is at F. Okay, so the gentleman, you are to work on between C and F. The boys, your work is objects between C and F. The girls, object is between, let me say between, it's at F. So use ray diagram to do this. When you finish, you share whatever you got with me. So boys, you have your work set. Girls, you also have your work set. Start work. And we are doing this within 5 minutes. Within 5 minutes. (8:25) exactly. Boys, objects between C and F. Girls between, so you can discuss. Boys, you can discuss. Girls, you can equally discuss on the page. Hey, you are not discussing, or you are discussing silently. Time is up. So let's discuss the word set for the boys. So place between, okay, before then, Kwabena, you are the leader of the boys. What were your observation? One. Kwabena Yameche.
Please. Image was virtual.
Kwabena had virtual image. Anybody? The boys. If you got any different nature, share with me. Kwabena got virtual. Aziz and the rest of you, Bright, Okine, Clef, and then World. Okay, so Kwabena, once image is virtual, clearly it will be upright. Is that right?
Yes, sir.
So upright. What again? What's the third characteristics? Kwabena, I'm listening.
So because, sorry.
Okay, we'll discuss it. So the girls, in your case, object is placed at F. Share with me the nature of the image you had. Ella. Ella, I'm listening.
Sir, please, my image was real.
Image real.
Then it was formed at infinity.
2. Formed at infinity.
Then say the image was inverted.
Once it's real image, it will be inverted.
And then my last one, it was magnified.
Magnified. Asada, what did you also get? Asada?
Please, I had the image to be real and was formed beyond the center of curvature.
Okay. Asada, I'm listening.
And since the image is real, it is laterally inverted.
Lateral inversion, you can't see it here. Because it's just a line object, you can't see lateral inversion. But what you can say is that it is inverted. Real and inverted. Asada, if you turn number 1, if you number 1 is laterally inverted, can you see? If I write 1 like this and it turns laterally, you can't see the difference. And so that's how come if you have an object like this and it's laterally inverted, you can't see any difference. Asada, do you get that?
Yes, please.
Bridget, say Bridget, Ohima, Hefziba, and the rest of you. Okay, so let's see what was given to the boys. We are not looking at who won, but all that we are interested in is just have a feel of the whole thing. Then when we discuss, you have the chance to identify your mistakes and your strength. Okay. So let's apply the rule. A ray of light parallel to the principal axis after reflection must reflect and pass through F. Any two rule would work. you don't need more than 2 to form an image. And you can choose any of the 4. So let me vary the rules. A ray of light from the objects here, okay, because I didn't take my measurement well, this rule will be difficult. Okay, so let me change it. A ray of light hitting the pole must reflect symmetrically. I'm only varying the rules. This will reflect symmetrically. This rule, you can also choose to vary, take measurements. So this angle here must be the same as this angle here. It doesn't look like that, so I'll vary it. Good. So when you are doing this, use straight edge to take measurement so that you get your angles right. That is, if this is the rule you chose. So incident, then reflected. Where the 2 reflected rays intersect, that will be where the image will be formed. By this, I can say that the image is real because it is formed either in front of the mirror or it is formed due to the actual intersection of reflected rays. Real and inverted. All real images are inverted. Then I can also say that image is magnified. Here, the size of the objects compared to the image is larger, so magnified. Then I can also say that image is formed beyond C, formed beyond C. So, Kwabena, this is how it must go.
Okay, sir.
So, identifying your mistake is what is important. When you vary the rules, you must get the same thing. I can choose to use this one instead. So, my first rule is a ray of light parallel to the principal axis must pass through F. I want to vary it. A ray of light passing through F after reflection must be parallel to the principal axis. So they will all give you the same results. It doesn't really matter the rules to choose. They will all give you the same results. Okay. Let's look at what was given to the girls. Yeah, girls question. Ohima, are you there?
Yes, sir.
And you don't even cough. Matthew, You don't even cough. Contribute, okay? So this is C, radius of curvature. Half of it is F. Object is at F. So apply the rules. A ray of light which is parallel to the principal axis after reflection must pass through F. Incident reflection. That's 1. 2. A ray of light hitting the mirror at 90. I'm coming. Let me rule the vertical line behind the mirror. Okay, because I did not take my measurement, applying this is difficult. So I'll choose a ray of light hitting the mirror at the pole will reflect at the same axis. Same axis. So this angle here must be the same as the angle there. I think that the angle between the principal and the reflected ray is bigger. So let me adjust it a little. That's why I said when you are doing this, you must take measurement. You see, here the two reflected rays are parallel to one another. And because the rays are moving in that manner, because the rays are parallel, it implies that they will meet at infinity. They will meet at a very far distance. They will meet at infinity. Why would they meet at infinity? Because the reflected rays are parallel to one another. Infinity is a very far distance. So let's even assume that infinity is here. Or the point infinity we are talking about is actually at this point. There is a point we are calling as infinity, very far point. So we are assuming that the two rays which are parallel to one another will be meeting at this point. I'm just assuming. we understand that where the reflected rays meet, that will be the point where the head of the image would be. So we are making the assumption that the rays are meeting at this point, meaning the head of the image will be here. The foot of the image and then the object is always on the principal axis. So let's trace the head to the foot. Good. So if the rays are meeting here, then we'll have the head at the point of their meeting. The foot will certainly be on the principal axis. By this, let's discuss the image. Let's discuss the image. 1. Image will first be formed at infinity. Image is formed at infinity. Asada, is this image real or virtual?
It is real
Why is it real?
because it is formed in front of the mirror.
It's formed in front of the mirror. 1. 2. 2. Why is it real?
It is inverted
Because it's inverted. 3. Why is it real? There is a third reason, which I told you about. Matthew,
Sir,
why is it real? The third reason why you think the image is real. Okay. Because it is formed as a result of the actual intersection of reflected rays. Actual intersection of reflected rays. Okay. All right. So once it's real, it will be inverted. Real and inverted. Kwabena, what again? What's the third observation? Kwabena, Bright. Cliff. What's the third observation? Aziz. Well, okay, so the last observation is that image is magnified. Look at the size of the objects and then the image. So image is magnified. So put this in your notebook. When an object is placed at F1, image is formed at infinity. Image will be real. Image will be inverted. And image is magnified. Class, are we okay?
Yes, sir.
Yes, please.
All right. Then, what about when the object is placed at infinity? You see, at F and at infinity, obey the principle of reversibility. Whatever happens in F will be reversed when you place it at infinity. So, the big question is that, how do I show that object is at infinity? Infinity is a very far distance. You cannot precisely determine the exact far distance. So in ray diagram, whatever we use to show that the ray is actually at infinity is this. And take note and write. Ella, are you there?
Yes, sir.
I've given you a question on that. That's why I'm putting you at the spot. I don't know if you still remember. So, Asida,
Yes, please.
have you identified any mistake? I remember I've given you this question earlier. You have submitted. But have you identified any error you made? Asida, I'm listening.
No.
But do you understand what I've just explained?
Yes, please.
Because in your submission, you were saying object will be formed beyond C. No. It must be the reflected rays will not meet. They will go parallel. And it is of this reason that we are saying if they are going parallel, then they will all meet at infinity. So when you draw it and the reflected rays actually meet, then you are wrong. Something went wrong. So find time and look at it. Now, how do we show that since we can't clearly tell that infinity is this point for us to place the object, to show that object is really at infinity, what we do is that the incident ray, the two incident rays hitting the mirror must come in that parallel form. So when image is at infinity, reflected rays must go parallel. When object is at infinity, incident rays must come parallel. So please take note that when image is formed at infinity, the reflected rays must be parallel to one another. And when object is at infinity, incident rays must be parallel to one another. So these are the keynotes. So I cannot precisely tell where infinity is, but to show that the object is at infinity, incident rays coming to make contact with the mirror must come in that parallel form. So one, I'm drawing a ray which is coming from whatever and hitting the mirror at 90. It must reflect along the same path and pass through that. Then two, I'm also going to draw a ray coming from somewhere, but I need to make sure that this ray is parallel to the first one. You just must ensure that the ray is parallel to this other ray, which is parallel to the first one, seems to be passing through F. And if it's passing through F, its reflected ray must be parallel to the principal axis. So the two incident rays must be parallel to one another. Now look at where the reflected rays are meeting. They are meeting at this point. Where they meet would be precisely where the image will be formed. Let's discuss the characteristics of the image form here. 1. Image form is, yes, image form is, Ella,
The image formed is real.
so real. All real images are
Inverted.
and inverted. 2. Two,
The image is magnified.
are you sure the image is magnified? Are you sure the image is magnified? Okay, to answer this, let me help you. We are saying that infinity is very, very far. So let's extend this line. And then even assume that infinity is at this point. So it means that if infinity, even if infinity is here, it means that these two incident rays are actually coming from the object which is here. So there's the head of the object. The foot of the object is always on the principal axis. So if this is the location we are calling as infinity, then the object is here. So this is the size of the object. So if this is the size of the object, and this is also the size of the image, is the image magnified or diminished, class?
Diminished.
Exactly. So image is diminished. And what is the final observation? What?
Image is formed
The image is
exactly
formed
at
by
F.
the
Exactly.
focal.
Hello? Hi, Waba. Okay. So image is formed at F. It's just the opposite of when it is at F. When object is at F, we saw that image will be formed at infinity. Formed at infinity. Image is real. And real images are inverted. And then we saw that it will be magnified. And so when you place it at infinity, object at infinity, yes, it's just the opposite of the same thing. Class, do we understand this?
Yes, sir.
Yes, sir.
Yes.
Aziz, you are not talking.
Yes.
I can also decide, instead of writing or drawing a power ray through F, I can also decide something different. I can choose a parallel ray which is incidenting on the pole of the mirror. All that I must ensure is that the two incident rays must be parallel to one another. And so if it is hitting the pole, then it must reflect at the same symmetry or angle. F is still here. It must reflect at the same symmetry. So check your angle very well. That's another way out. So incident reflected. So in books, you sometimes see this. When the rays are coming in that parallel manner, they write objects at infinity. Object at infinity, just because the two rays are parallel to one another. So this is where the reflected rays intersect. And you can see it is precisely on the principal focus. So simple. Is there any question? Is there any question, class? So we've discussed every position. Note that the only time concave mirror, a concave mirror would form a virtual image is when the object is placed between the pole of the mirror and then the principal focus. It occurs only once. The only time a concave mirror forms a virtual image is when object is placed between the pole and the focal point. All other positions, you get a real image being formed. If you have any question, quickly ask before we discuss convex mirror. Asida, ask your question.
Yes, I don't have a question.
Yeah, Kwabena Yamiche, ask your question. Matthew, ask your question. And the rest of you. Okay. Then let's quickly look at, if it is convex, how will this... For convex, every position of object would give you a virtual image. So for convex, we don't vary positions of the object, because no matter the object position, the image formed would have the same characteristics. So it reduces our work in convex mirrors. But so let's draw for about 1 or 2. Curves, reflecting surface, curves outwardly. Let me extend it at the back a little. So this is the pole. Let's assume focal point is here. C is also here. Let's bring the object closer to and when we finish, we'll take it back to C. So let's apply the rules. A ray of light parallel to the principal axis will be diverted, and the diverted ray appears to be diverted from F. Benjamin, clear your clouding from our diagram and leave the board alone. So this is the reflected ray. The reflected ray always appears to be diverted from a point on the principal axis. 2. Let me change the color. A ray of light hitting the pole must reflect symmetrically. So incident reflected. When you look at the two reflected rays, 1 and 2, would they possibly meet in front of the mirror? Class, would they ever meet in front of the mirror?
No, sir.
No. Meaning, there's no way a real image will be formed in front. So let's trace back the path of the reflected rays. So usually, we trace the broken line to the center of, to the focal point, and they intersect here. Where they intersect, that is where the image will be formed. So let's discuss this image. 1. Aziz, 1. We are discussing the image.
It is virtual
It is virtual. Aziz, why is it virtual?
because image is formed at the back of the mirror.
That is 1. Or, why is it virtual? Or, anybody else? As to why
The image is erect.
and we want to talk about why it is okay, fine. I understand you. The image is erect, or this image is formed as a result of the apparent intersection of reflected rays. Apparent intersection of. So the reflected rays appear to intersect at this point. That is why, okay. So image is virtual. All virtual images are erect or upright. Three. Virtual, erect, or upright. 3. Oh, wealth. Benjamin. Express your views. If wealth is not wealthy, somebody else should come in. Matthew, we are discussing the characteristics. Bright. Bright, go ahead. Bright cannot brighten up. Ella.
Say, please, the image is diminished.
Image is diminished because the object size is greater than the image size. As that the final one.
The image is formed between P and F.
P and F. Yes, you are not wrong. But here, because it's virtual, it is formed behind the mirror, at the back of the mirror. Okay? Or the location of the image is opposite to the location of the object. So formed behind the mirror. You see, for convex, because all measurements behind the mirror is virtual, we don't look at between P and F, F and C and all that because they are virtual points. They are not actually there. But we talk about that in concave because these are real points. As that, are you okay?
Yes, please.
Okay. Class, is everybody okay with this part? Because I'm going to vary another position of the objects to see how the image will look like. So if you are okay, can I carry on?
Yes, sir.
All right. So I'm going to this time place the object very far and use the ray diagrams. So this time the object is very far from the mirror. Let's still use the ray diagram to see how the image will look like. So a ray of light parallel to the principal axis will be reflected, and then the reflected ray always appears to be reflected from a point on the principal axis. So incident reflection. A ray of light which hits the mirror at 90 would appear to pass through C. So every measurement or ray at the back, please use broken lines. I repeat, I do not have that here. That's why it's a solid line. So all these points must be broken line because they are virtual. The two reflected rays, so incident, reflected. The two reflected rays appear to intersect at this point. image is still virtual. One, virtual. You see, we have varied the position, but the image is still virtual. It's still erect or upright. When you compare the image size to the object size, still image is diminished. Still, it is still formed behind the mirror. And as that, you see, no matter, you see, we change the object to a far distance, but it is still, its location between the pole and F doesn't change. So that is why we don't even talk about that, because no matter the object position, this location doesn't change. So form behind the mirror or opposite to object position. So for convex mirror, no matter the object position, you get the same characteristics of the image formed. And it is of this reason, this is very important. When you look at driving mirror, the side view mirror, or the rear view mirror of cars, there is always the statement that objects seen in the mirror is always closer than the real situation or so. Please, have you seen that writing on mirrors, side view mirrors of cars? Class, I'm asking a question. Have you seen that in mirrors? There's always the inscription that objects seen in the mirror appears closer than they actually are. Kwabena Nyameche, Matthew, have you seen that in side view mirrors before? Such writings in side view mirror.
Please, I can't get because of the rain. Sorry.
Okay. There is that writing because, you see, objects in mirrors always, no matter the image formed by convex mirror, no matter the object position, is always closer to the mirror. When we brought the object closer to the mirror, the image was between PF. We took it far, the image is still between PF. You can take it very, very far. You can bring the object here. Still, you can choose to bring the image very far. As I said, the object very far. Its image will always be formed between P and F. So it means that the images formed by a convex mirror is always closer to the mirror. So that is why there is such writing on side view mirrors. Objects you see in the mirror is always closer than they actually are. And this image position always helps reverse driving. When you are reversing and you see image of objects in the mirror, because the image is always closer to the mirror, you may think you are hitting the objects, but in reality, you are not there yet. You thinking that you are so close to the object and so apply the brake to stop, it's an advantage. So it means you will stop before you actually hit the object. So this serves as an advantage in reverse driving. So it is of this reason. So exams, you can be asked, explain why there is the inscription that objects or image or object in mirrors are always closer than they actually are. And this is the reason. The image formed by a convex mirror is always closer to the mirror, no matter the object position. If you have any question, quickly ask. Okay, so that's it. This is the nitty-gritties of images formed by concave and convex mirrors. The nitty-gritties of it. So you must master all positions for concave mirrors or mirror, and you must also, as for convex, the image is always the same no matter the object position. Image will always be virtual, erect, diminished, and formed behind the mirror. All right. The next thing we must look at under this would be, I'll introduce you quickly to mirror formula before we look at refraction of light. So we'll go through mirror formula. The mirror formula. Please, this mirror formula thing only applies to spherical mirrors and not plane mirror. The mirror formula. Are you people tired?
Yes.
Those,
The girls are not talking. It means they are tired. Ella, are you tired?
No, sir.
Asada, you can't be tired. You just came. As for Hepzibah, whether she's tired or not, she can't even say it because her microphone is not working. So I presume she's not tired. Then, Ahima, Anumboye stable, the network. So I'll take you through the mirror formula briefly. So see. Practically, mirrors have small aperture. So let's even reduce the aperture and then rule vertical line behind it. So you don't draw a bigger mirror, no. Just a small one with the vertical line at the back to cater for reflections beyond the aperture of the mirror. Let's place the object. It can be any other position, but I am choosing to place the object at C. Okay, let me vary it. Object is beyond C. So let's use a ray diagram to form an image of this object. So objects, ray parallel to the principal axis after reflection will pass through F. Then a ray passing through F after reflection must be parallel to the to the principal axis. So incident, reflection, incident, reflection. The image is formed here. Now, the distance from the mirror to the object. This is the object distance U. The distance from the mirror to the image. This is also the image distance V. The distance from the mirror to the principal focus. This is the focal length F. Let's label this point. Let's clear the center of curvature because we are going to represent letters and it will confuse us. So O, A, F is already here. There's a point B, C. Let's call this point D. We already have F. Then let's call the image point I. Then this point, let's call it J. So we see a lot of similar triangles. Similar triangles in here. When triangles are similar, one, they are just a magnified or demagnified version of one another. So, two, when triangles are similar, their interior angles, corresponding interior angles are the same. Let me show you how you can identify it. You see, when you look at triangle OAF, which is this triangle, OAF, its similar counterpart is triangle FCD. Why are they similar? They are similar because this angle of OAF is equal to this angle of FCD. Vertically opposite angles are equal. This angle, which is 90, must be the same as this angle here, which is 90. In fact, mirrors are 3. That's why I said just a small aperture. So it just appears like a plain mirror, but because it curves. So if this is 90, this is also 90. Then this angle here corresponds to this angle here. So OAF and FCD are similar triangles. Class, are we okay?
Yes, sir.
Because they are similar triangles, the ratio of their equal sides, the ratio of their same sides must be equal. must be equal. What do I mean by the ratio of their same side? If I take AO, then I take the equal size of their equal similar triangle, which is this. AO, this point is already even the pole. So let's even maintain it. This point is the pole. So AO over PD must be the same. This is equal to OF over FP must also be the same. Asida, Ella, and the rest of you, are you okay?
Yes, please.
Yes, please.
Okay. So this is 1. Now what is OF? AO. AO is the object height. H subscript O. Object height. What is PD? PD is just side, but this vertical height is the same as the height of the image, which is this. So this is HI. So PD is the same as image height. So H subscript I. Are we okay? Are we following?
Yes, sir.
please.
What is OF? Let me guide you. OF is this distance. You see, but we have OP, which is equal to OF plus FP. OP is the same as the object distance, isn't it? OP is the same as the object distance. Class, are you okay? So OP is the object distance, the distance of the object from the mirror. So this is U, which is equal to OF, we don't know. That's what we are looking for. But what is FP? Class, what is FP? I'm waiting for you. What is FP? Yes, Ella.
Sir, please, is it the focal length?
That's the focal length. That's why I represented that distance by F. So FP is the focal length of the mirror F. Therefore, we can say that OF is equal to object distance minus the focal length. So U minus F divided by FP, which is also F. This is equation 1. Please ask questions if you have one. Let's identify another similar triangle. So triangles are similar when they have the same interior angles and when a ratio of their equal size are the same. So I want somebody to help me identify another interior angle. I represented this by I, so let me put it there. Help me identify another similar triangle after OAF and PCD. Yes. If you delay, I'll call, so hurry up. If you delay, I'll call individually. Okay, so once you are delaying, Asada, help me identify another similar triangle.
Triangle AFB and triangle FJD.
Asada, take your time. Triangle
AFB.
A F F. Oh, you are right. You are right. But you see, this one we don't have a representation for the slanted sides. So ignore those triangles where we use the slanted side. We don't have any representation for it. Asada, do you understand?
No, please.
No, what I'm saying is that look at AF. We don't have anything to represent this distance AF. BF. We don't have anything to represent it. Okay. FD. We don't have FJ. So the slanted sides, we don't have something to represent. Even though they are similar triangles. That's why I'm asking you to disregard it and pick a different one. Yes, Ella, I saw your hand raised earlier.
Purple is triangle IFG and
Let me write it. FJ and
triangle BFP.
BFP. The gentlemen, are you following? Matthew,
Yes,
Aziz,
sir.
who is gone? Aqua Aziz
Yes,
is
sir.
here. Clef is here. Hepzibah, I think, oh, I've forgotten his name. So this choice will do because when we look at IFJ, we can have whatever we want. Okay, so you see their interior angles are equal. This is equal to this. This is 90. This is also 90. Then this angle would correspond with this one too. All right. So if they are similar triangles, then the ratio of their equal size must be equal. So IJ over BP must be equal to IF over FP. You see, as that we are ignoring their slanted side because we don't have anything to represent that. Okay. Now, what is IJ? Class, what is IJ? I'm waiting. What is IJ?
Image.
The image height. Not just the image height. So this is H subscript I. What is BP? BP.
Object height.
Thank you. IF. IF. IF.
The image distance.
Sorry, IF is not the image distance. The image distance will be IP instead, which is still the same as JD. But what is IF? It is part of something, so think wide. Munkaya yankoye. IF.
Please, is it the center of curvature?
No, I even cleared the center of curvature. IF. I think it's a part of a bigger one. So think and answer. When you see the trick, raise up your hand and share. Monka ya yankwai. Yes, Kwabna Yameche, Cliff, Matthew, and the rest of you.
Yes, sir.
IF. Yes, Ella.
Sir, please, IP minus FP.
So IP minus FP. Ella, what is IP?
Mhm. Um,
What you are saying is very, very true. What is IP? IP is the image distance V, isn't it? Look at the image distance. So IP, the same as JD. So IP is the image distance V. Class, are you with me?
Yes, sir.
Minus, what is FP? What is
it's
FP? Pardon?
F.
That's F. So IF is actually V over F divided by F. And this is equation 2. So we have equation 1, which is H O over HI equal to U minus F over F. Okay. Now we want to turn equation 1. This is HI over HO. We want to turn equation 1 to also have the ratio HI on HO. As it looks, okay, they are not the same. So we want to make image height, object height be the same. So HI over HO from equation 1 will be equal to F over U minus F. The same equation 1. Class, I hope you are following. Class, are you following?
Yes, sir.
So once the left-hand sides are the same, then we can equate their right-hand side. So because this is now equal to this, then we can say that then V minus F over F is equal to F over U minus F. Let's cross multiply. So when we cross multiply, we have V minus F times U minus F equal to F squared. Help me expand the left-hand side equation. Expand the left-hand side equation. Are we done? Are we done? Hello, you are wasting time. Give me feedback. Are you done?
Yes, sir.
So expansion of this will be UV minus VF minus UF plus F squared, which is equal to F squared. This and this will go to 0. So we have UV equal to, when all the negatives crosses the equal sign, we have VF plus UF. This must be the final thing you have. Are you all getting this? If you get this, tell me so we continue.
No, please.
Where have you reached?
Please,
Have you,
can you
Mhm.
please can you begin from the expansion again?
You are expanding this. Let me clear. When you cross multiply, you have this is equal to F squared, isn't it? In expanding of this, take V, multiply V by U minus F, take minus F and multiply it by U minus F, equated to F squared. So V times U is either VU or UV, whichever way you want to call it. Then V minus V times negative F will be minus VF. F times U minus UF. Negative F times negative F, you have plus F squared. This is equal to F squared. Is that okay?
Yes, please.
Then when you group like terms, F squared minus F squared, this will reduce to 0. You let all the negatives cross the equal sign. So you have UV is equal to negative, this will become positive. So VF plus UF accordingly. Then when you finish, divide each side, divide through by UVF. So divide every member of this by the product UVF. So I'm going to do that. So UV divided by UVF is equal to VF also divided by UVF plus UF divided by UVF. So I'm dividing each term by UVF. So UV will cancel out this. VF will also cancel out this. UF will cancel out U and will cancel out F. So what will be left is 1, the left hand side you have 1 over F is equal to 1 over U plus 1 over V. This is the famous mirror equation. So we have derived the famous mirror equation 1 over f is equal to 1 over u plus 1 over f, where f is the focal length of the mirror. Focal length. U is the object distance. V is the image distance. As disciples of physics, you must learn how to derive the mirror formula. The mirror formula. If you have any question, ask. If you don't have any question, we'll end here. But you must spend time to go through this and master how to derive the mirror formula. It's not difficult. Just go through what we've done, and that's all. Okay?
Yes, sir.
All right. So if you don't have any question, this is where we'll end today's show. I'll fix, okay, we have lesson on Monday. We'll fix another day to make up for last week's loss. Okay, bye-bye to each one of you. But please go through the how to vary objects to form the image in spherical mirrors. Okay, as well. Bye-bye.
Thank you, sir.
Welcome. Can I leave the page, or some of you are still writing? Okay, so there's no talking. It means you are done. I can leave.